All right, let's get some practice working with word problems in trigonometry. The first topic we're going to look at will be angles of elevation and angles of depression. Now, anytime we measure an angle of elevation or depression, they always have to be measured from a horizontal line. So if I'm looking at something being elevated, I care about how many degrees it's angled up from whatever horizontal would be. Same with depression. If I'm measuring an angle of depression, it needs to be measured from a horizontal line. The difference between an angle of elevation and an angle of depression is that elevation measures upward angles and angles of depression measure downward angles. So as an example, let's say we've got a squirrel that's hanging out on the ground, maybe over here, and he's looking at an acorn that's up in a tree, hanging out about up here. And I know that the angle of elevation from that squirrel to the acorn to be 37 degrees. So I label the angle of elevation here in blue. It's 37 degrees up from the horizontal line. If I know that that angle of elevation is 37 degrees from the squirrel to the acorn, I also know that the angle of depression from the acorn back down to the squirrel is also 37 degrees. But I need to measure that line, or I need to measure that angle from a horizontal line. I just draw one in real quick. I could say I know that this angle of depression is also 37 degrees. So anytime I'm looking at the same two objects, if I know the angle of elevation from one to the other, that means I also know the angle of depression in the reverse direction. And again, these should always be measured from horizontal lines. So let's put that into practice. Problem 10. April is lying on the beach flying a kite. She holds the kite string at a diagonal and she estimates the angle of elevation of the kite to be 58 degrees. If the string she's holding is 420 feet long, how high is the kite above the ground? So if we come through and label some of the stuff that we know, we had a 58-degree angle of elevation. So we know that this angle is 58 degrees. Additionally, we know the string is 420 feet long. So I know that that length, that hypotenuse, is going to be 420 feet. Finally, I'm looking for how high the kite is above the ground. So I'm going to look for this height, h. Now, if I take a look at this triangle, I know an angle, being 58 degrees, I know a hypotenuse, and I'm looking for the side that is opposite my angle. So I want something to relate the opposite side and the hypotenuse together, which means I'm looking at sine, since sine is opposite over hypotenuse. So sine of 58 degrees should be equal to h over 420, meaning that that height is 420 times the sine of 58 degrees. We can plug this into a calculator, and if we do, we're going to want to round to 0.01 decimal places. So 2 decimal places is what we're going to want to round to. If we notice back to the directions of the problem. So if we're using a graphing calculator, make sure that you are in degree mode, since we're plugging in 58 degrees. But I popped that in and I got 356.18. And that should be in feet. Problem 11. A news anchor is standing 210 feet from the base of a Miami construction tower with a crane attached to the top. The angle of elevation from the news anchor to the top of the crane is 76 degrees. How tall is that construction tower? So, labeling what we know once again, our angle of elevation is 76 degrees. So this upward angle from the horizontal line should be 76 degrees. Next, we know that news anchor is standing 210 feet away. So I should label that bottom side as 210 feet. And I'm looking for the height of that tower. So H for height over here. Now I know an angle, I know the adjacent side is 210, and I'm looking for the opposite side. So I want a relation between an angle, the opposite side, and the adjacent side. That should be tangent. Since tangent is opposite over adjacent. Tangent of 76 should be equal to H over 210, meaning that H is 210 times the tangent of 76 degrees. Plugging all that into a calculator, I got 842.26. Once again, we're measuring in feet. Okay, problem 12. Ron's eye level is at 6 feet. Ron noticed that one of Andy's shoes is untied. The angle of depression from Ron's eye to Andy's shoe is 54 degrees. How long is the line of sight from Ron's eye to Andy's shoe? So we have another fancy diagram drawn down here, but this time we're going to look at the angle of depression instead of the angle of elevation. So I've drawn in the eye line with a line of sight from Ron's eye over to Andy's shoe. But in order to draw the angle of depression in, I'm going to need a horizontal line. So I'm going to come up here to Ron's eye level, draw on a horizontal line, and then label that angle of depression to be 54 degrees. Since I know that that angle is 54 degrees, that angle of depression was 54 degrees, I also know the angle of elevation is 54 degrees. I also know that Ron in all his mustachioed glory is 6 feet tall, so I can label this side over here to be 6 feet. Additionally, I could know that on the left side of that triangle that I've drawn in, I could also have 6 feet over there. Either way, though, that 6 feet is going to end up opposite my 54-degree angle, and I am looking for that line of sight, which let's just label it C. So looking for the length of that line of sight, I know an angle, I know an opposite side, and I'm looking for a hypotenuse. So I want something to relate opposite and hypotenuse, which would be sine once again. So sine of 54 degrees is equal to my opposite side, which is 6, over my hypotenuse, which is C. Solving this one, I'm going to get that C is equal to 6 divided by sine of 54 degrees. Plugging that into a calculator, I got 7.42 feet. Problem 13. Leslie is standing 21 feet from artwork in a gallery. She notices that the angle of depression from her eyes to the bottom of the artwork is 14 degrees, while the angle of elevation from her eyes to the top of the artwork is 7 degrees. Find the height of the artwork. So in this problem, we're going to be using both an angle of elevation and an angle of depression to solve two parts of the same problem. So we noticed that that angle of depression, which should be the angle measured down, was 14 degrees, while the angle of elevation, which is the angle that should be measured up, should be 7 degrees. And notice that on both of these angles, I'm measuring them from a horizontal line to the piece that I'm interested in. And I'm going to have to split this up into two parts, since I'll be looking at two different heights that I'll then add together. So let's call height 1 this little bit that's from Leslie's eye line to the top of the painting. Then we'll also label a height 2, which will be the distance from Leslie's eye line down to the bottom of the artwork. We also know that she's 21 feet away, so this line right here in the middle should be 21 feet. Now, in the blue triangle, so the triangle that's on top with an angle of elevation, I'm looking for the opposite side and I know the adjacent side, which means I'm going to want to use a tangent equation. And for the bottom triangle, the red triangle that has an angle of depression, I'm again looking for the opposite side, h2, and I know the adjacent side is 21, so we'll use tangent for that triangle as well. We get the equations tangent of 7 degrees is equal to h1 divided by 21, meaning that h1 is 21 tangent of 7 degrees. Also, the equation tangent of 14 degrees is equal to h2 over 21, meaning that h2 is 21 tangent of 14 degrees. Putting all that together, the height of that painting is going to be equal to h1 plus h2, which should be 21 times tangent of 7 degrees plus tangent of 14 degrees. Since I can factor that 21 out of both h1 and h2, which gives a height of 7.81 feet. All right, the next few problems we're going to try to simplify using those trigonometric identities that we had at the beginning of the worksheet. So in 14, 5 times sine squared of 28 degrees plus cosine squared of 28 degrees. Well, sine squared plus cosine squared is an identity. I know that that's equal to 1. So my simplified answer would be just 5. 15, 3 cosine 5 degrees times secant of 5 degrees. I know that secant is the reciprocal of cosine. So this should be 3 cosine of 5 degrees times 1 over cosine of 5 degrees. Those two cosines simplify with one another, leaving me with just 3. In problem 16, I have secant squared of 53 degrees minus tangent squared of 53 degrees minus 1. I know from my identity that one of the Pythagorean identities, that 1 plus tangent squared is equal to secant squared. So secant squared of 53 degrees should be 1 plus tangent squared of 53 degrees. Then still minus tangent squared, 53 minus 1. And that should all simplify to 0. 1 minus 1 is 0. tangent squared of 53 degrees minus tangent squared of 53 degrees, also 0. 17 is where things get a little interesting. I have two different angles in problem 17. And anytime we're working with two different angles in this same trigonometric identity problem, we're going to want to change one of them. Now, most of the time, as we look through some of these example problems, because they're being set up a special way, anytime I'm giving you two separate angles, they should almost always work out to be complements of each other. So if we notice here that 16 degrees plus 74 degrees should be equal to 90 degrees. So because I have complementary angles, I should be able to use a cofunction identity to change back and forth between them. The cofunction of cosecant would be secant, since cofunctions switch back and forth between a function and its cofunction. So secant and cosecant, meaning that the cosecant of 16 degrees should be equal to the secant of 74 degrees. And since it was cosecant squared, I'll have secant squared. So again, the cofunction identities will switch back and forth between a function and its cofunction, and also an angle and its complementary angle. So cosecant squared of 16 degrees is the same as secant squared of 74 degrees. Fill in the rest of the problem. And I have secant squared 74 degrees minus tangent squared 74 degrees. Which is nice because now both trig functions have the same angle, so I can start using those trig identities. And I know from the Pythagorean identity that secant squared minus tangent squared should be equal to 1. If I just rearrange that equation. All right, same thing in problem 18. I have 80 degrees and I have 10 degrees. And 80 degrees plus 10 degrees is 90 degrees. So I have complementary angles once again. So I can use a cofunction identity to change one of these functions. So in the last problem, I changed cosecant and secant using a cofunction identity. This time I'll change sine into cosine using a cofunction identity. So the sine of 80 degrees should be equal to the cosine of 10 degrees. Since if I change from a function to its cofunction, I should change the angle to its complementary angle. So an angle to its complement. So 2 cosine 10 degrees times secant 10 degrees. I just finished out the problem. And then all of my angles are the same, meaning I can apply the rest of those trig identities. Here we'll use the fact that cosine and secant are reciprocals of one another to say that this is 2 cosine 10 degrees times 1 over cosine 10 degrees, which simplifies to 2. Problem 19, again, we're looking at complementary angles. 20 plus 70 is 90. Kind of looks like 76. So this time, since I have multiple angles, I'm going to change the one that'll require me to do the least amount of work. Since I already have 20 degrees appearing twice, I'm going to change the 170 degree angle to show up as a 20 degree angle, again using a cofunction identity. So tangent already has 20 degrees, so I'll leave it alone. Times cosine already has 20 degrees, so I'll leave it alone. So it's just that guy on the bottom that I want to change. So I'm going to change from cosine to its cofunction, which is just sine. So I'll need to switch from the angle to its complement. So tangent 20 degrees times cosine 20 degrees over sine 20 degrees. So I just changed cosine 70 to sine 20. Then I can use one of the identities for tangent to say that tangent 20 degrees is equal to sine 20 over cosine 20 times cosine 20 over sine 20. Here, basically everything simplifies. I have sine over sine, both of 20 degrees, which is just 1, and I have cosine 20 over cosine 20, which is also 1. So in the end, everything simplifies to 1.